Alright, so we're going to begin our discussion on kinetic energy with the Physics Science 10 unit. Let's get going. Kinetic energy is the energy of motion. When anything is actually moving, it has kinetic energy. Now, kinetic energy is dependent on two separate variables, speed and mass, and it's given to you in this wonderful little formula here. Okay? So in this formula, EK is the kinetic energy in joules. Remember the joules unit from when we started talking about work. Mass, again, in kilograms, same as before. And V is the speed in meters per second. Okay. Now, common things people forget about in this formula are these two little components here. Number one, you can't forget about the squared that's on the speed, as well as the half that goes into this. Common mistakes people make are to forget these in the calculation, and it will drastically change your answer. So recall that work is a force which makes something move. Okay, so again, when we apply a force to an object, we are doing work. Okay, so when we apply a force to the box to push it across the floor, we are doing work. Okay, if kinetic energy is put into an object, work is positive, which means that the speed will increase. The more work we do to an object, the more speed we get. Okay, if kinetic energy is removed, okay, work is a negative value. And we saw that in one of our examples previous. Okay, which means if work is negative, speed decreases. So let's take a quick look at our skateboarder in the half. So here's our little skate park, and we're going to demonstrate exactly how these variables play into each other and how kinetic energy changes as we go through. So as we put the skateboard on the top of our little half pipe, we can see we have a lot of potential energy, which we're going to talk about in the next little section. Okay. Now, again, as you can probably assume, if I let go of the skateboard, he's going to roll down the ramp. Okay. As he rolls down, we can see the kinetic energy and the speed both increase until he reaches the bottom. Okay. So what we'd end up seeing at this point, okay, going down to the very lowest part, we'd have a positive work value. Speed is increasing. But as we go up, friction takes its role, and we'd have a negative work value as the speed decreases as he reaches the top. So let's head back to our presentation here. So let's look at some examples of actually using this formula. We need to make sure we practice a lot for this, as this is stuff you're going to see quite regularly. So what is the kinetic energy of a 680 kilogram grizzly bear running at 14 meters per second? Okay, we can take a look at the important values in this question. Okay, we know 680 kilograms and 14 meters per second. Okay, kilograms is a mass unit. So we'll record that as our mass, 680 kilograms. Okay, whereas the 14 meters per second is our velocity, because we know meters per second tells us velocity or speed. Okay, now we are looking for our kinetic energy. Okay, so let's start by writing out our equation, which will be given to you, okay, mv squared. Okay, when we plug everything in now, we have m, we have v, we see 1/2 times 680 kilograms times 14 meters per second squared. Okay, so when you're typing this into your calculator, it's probably easiest to do this little section first. So you type 14 squared, gives you a number, and then times it by 680, and then divide it by 2 to give you an answer of 66640 joules. Okay, since significant digits still matter, we only have 2 significant digits. Okay, so what we end up seeing, we have to cut the number off here. Okay, so we're going to change this into scientific notation, which we've done in class. 6.7 times 10 to the 4 joules. And that would be our final answer. Okay, so let's try another example. So a bullet with a mass of 0.05 kilograms is fired with 16,000 joules of kinetic energy. What is its speed? So as you can probably already try to figure out here, we have a little bit different of a question. It requires a different variable than the last one. So, just like any other question, we write out what's given. We have a mass, 0.050 kilograms. Okay, we have 16,000 joules, which would be our energy term. And now we know we're looking for speed. So again, when we write out our equation now, 1/2 mv squared, okay, this time we are looking for our v term. Okay, so what do we need to do? We need to move the 2 to the other side by multiplying. So we end up seeing 2ek is equal to mv squared. Okay, now we got rid of the 2 over there. We want to move m over, so we need to divide by m by both sides. Okay, and now we have 2ek over m is equal to v squared. Now the biggest question you're probably asking is, how do I get rid of this guy? Okay, so again, the opposite of a square is what we call a square root. So you're going to take and you're going to square root both sides. Okay, so now our equation is going to look like v is equal to the square root of 2ek divided by m. Okay, now we have a formula that is finding what we are looking for and uses the variables we have. So now we easily just plug in and solve. 2 times 16,000 joules divided by 0.050 kilograms gives us a final answer of 800 meters per second. Okay, so 800 meters per second. Now we need to make sure that we're okay with significant digits. In our calculation, we have 2 significant digits limiting us here. Okay, so we need to cut this off at 2 significant digits, so we're going to put it into scientific notation, 8.0 times 10 to the 2 meters per second. And that would be our final answer. So key things to remember with this formula is you need to make sure you know how to manipulate this energy equation. This is probably one of the trickier ones that we are going to have to change. So you need to make sure you know how to do these steps. So let's move on. So when a 52.0 kilogram cheetah is running at 112 kilometers an hour, what is its kinetic energy? Okay, part A. Part B, how fast does a 3.20 times 10 to the third kilogram hippopotamus have to run in order to have the same kinetic energy? So let's look at part A. Okay, what are we given? We're given a mass term, 52.0 kilograms, and we are given a speed. Okay, a speed of 112 kilograms per hour. Kilometers per hour, sorry. Now, what you're probably already noticing is, hey, this is not in the units that we need. We need meters per second, so we need to do some conversions first. Okay, so to convert this to, in order to convert this to meters per second, we're going to use some dimensional analysis. Okay, so we know we have to convert using the meters per kilometer. Okay, we know that there's 1,000 meters per 1 kilometer, which will change that unit for us. Now, we have to focus on hours. Okay, so we know how many minutes there are per 1 hour. Okay, which obviously is 60. And then again, we see there's 1 minute per 60 seconds. Okay, so again, we see all of these units cancel out. This is nothing new what we've covered in chemistry. Okay, so now we have meters. We have meters per second, which is exactly what we want for our answer. So the way this works is we go 112 times 1,000 divided by 60 divided by 60. Okay, to give us a speed of 31.1 repeating meters per second. Okay, now we can use that into our regular calculation the same way as before. Makes it a lot easier if we can convert this first. Okay, now if we're trying to find the kinetic energy, we just use our formula, 1/2 mv squared. We plug in 1/2 times 52.0 kilograms times 31.1 meters per second, the square value, and we end up getting an answer of 5.61 meters per second, all said and done with the significant digits. Oh, sorry. I wrote down the wrong numbers. Give me 1 second here. What we end up getting is 5.61 5.608 times 10 to the 4 joules, which we're going to carry into the next calculation. Okay, so that answers part A. We found the kinetic energy. Now, part B, we need to take a look at again. Okay, so if we scroll back up to the top, we know this time we have a mass. We have a mass that's equal to 3.20 times 10 to the 3rd kilogram. And what we're assuming here is that their kinetic energies are going to be the same. So we're going to be using this answer that we had up here in the next question. So 5.608 times 10 to the 4 joules. Okay, and this time we're going to be looking for speed. Okay, so we are going to plug into our equation. Okay, so we're going to be using the same one we did before. EK to the 1/2 mv squared. We're going to rearrange that to solve for v. So v becomes square root of 2ek over mass. We'll plug in 2 times 5.608 times 10 to the 4 divided by our mass of 3.20 kilograms times 10 to the 3 kilograms to give us a final answer of 5.61 meters per second. Okay, so again, you can obviously see the pattern that's here, right? The hippopotamus is significantly heavier, it has to run a smaller velocity in order to match the same kinetic energy as the cheetah above. Okay, so there's a direct relationship between these two variables. Okay, the driver of a 1,500 kilogram car, okay, traveling on a highway, hits the brakes. A force of 12,000 newtons stops the car at a distance of 64 meters. How fast was the car going when the driver hit the brakes? So we kind of have to work backwards a little bit here. So let's write down our important variables. Mass, 1,500 kilograms. Force, 12,000 newtons. Distance, 64 meters. And we are looking for a speed. Okay, so again, we know work has both the force and the change in distance in it. Okay, what we have to assume in this question is, like we talked about, work is just the application of energy. Okay, so when we put a certain amount of energy, or when we do work in a system, we are converting that work into energy. So what we can assume here is work is equal to our kinetic energy. Okay, so that's our first step to find. We know force, we know the change in distance, we can find our work. So that's what we'll do first. 12,000 newtons times 64 meters, okay, gives us 7.68 times 10 to the 5th joules. So we're going to take that number into our next calculation and find our speed using the same formula we had before. 2ek over mass. Okay, so we're going to take this, 2 times 7.68 times 10 to the 5th joule divided by our mass of 1,500 kilograms. Okay, this, when we plug it into our calculator, comes out to an answer of 32 meters per second. All said and done with significant digits. If you're confused on how to come up with this formula, refer back to the video a little bit. You can pause and rewind. So again, we've used a little bit of kinetic energy in different forms here. You just have to make sure you have an understanding and link the connection between work and energy. When we put work into a system, we're putting energy into it and transferring it into kinetic energy. Okay? So take a few seconds, write down 4 or 5 key points in this video, and bring them to class tomorrow, and be prepared to do some practice. Thanks for your time. Talk to you later.